Thank you very much, Tracy. Can everybody hear me? I'm going to take the silence as yes. No, there's no shaking heads. Yeah, so thanks a lot, Tracy, for the introduction. Thanks to everyone for inviting me to give this talk today. I'm a newly minted faculty member at MGH. I started in July. I did a neurocritical care fellowship, as well as a neuro rehab fellowship. So I'm 3 years out of my neurology residency, which I completed in 2017. I'm going to tell you a story today about sort of work we've been developing around stroke recovery over the past 4 years at MGH. We've been collaborating with folks at Hopkins, specifically on Preeti Raghavan, who I think will join the call when she's out of clinic. And so the story sort of I'm going to tell you is as much sort of an origin story as it is a science story. I have no financial disclosures. So the outline for today is I'm first going to talk about stroke recovery as a health systems problem, which I think many of you in the PM&R field will be familiar with. I'll talk about outcomes as well as biomarkers for upper extremity stroke recovery. And then I'll talk about sort of how we're thinking about the future of stroke recovery in terms of treatments. So this is the view from the MGH helipad. This is a helicopter out in the distance. This is a helicopter landing on our helipad, and this is me while I was a fellow on acute stroke call. This is a patient who's being brought from New Hampshire to MGH. As I'm sure is also the case at Hopkins, MGH is a major coordinating center for acute stroke. And so many of the patients that we receive have received TPA actually at the outside hospital and are flown to MGH for consideration of endovascular therapy. And so that's where a neurosurgeon or a neuroradiologist goes in with a stent retriever to try to retrieve large M1 clots. And so as this crowd I'm sure is familiar with, the last 10 years, even really during the time of my own training, has been transformative for acute stroke. From the advent of TPA in 1995, the NINDS trial, to more recently in the last decade, really 2015 and forward, endovascular treatment where large strokes can be removed has been really transformative for this field. It's changed the way that we think about stroke systems of care. It's changed our metrics, et cetera. But the truth of the matter is, as you guys know, only 1 in 20 patients are treated in time for acute stroke therapy. And as a result of that, stroke remains a leading cause of adult disability in the United States. Despite rehabilitation, a significant number of stroke patients remain severely disabled. And I'm going to talk about arm motor impairment as sort of a model for thinking about stroke recovery, because it seemingly, well, the first is that it's a major source of disability. And the second is that seemingly it seemed like a relatively straightforward, quantifiable model for thinking about recovery after stroke. It turns out that it's complicated, as we've learned in the last many years, but we thought it was a good starting place. And in contrast to the sort of transformative advances in acute stroke therapy, really our treatments for stroke rehabilitation have remained limited. And really in the last 50 years, the kind of cornerstone of rehabilitation after stroke treatment remains PT, OT, and SLP. And novel therapies sort of have not crossed the borderline. And I'll talk about reasons why we think so in later slides. And so the fundamental question that drove much of my research program over the last 4 years is the question that all patients ask when they come to the acute stroke ward, but as neurologists, we feel that we're least equipped to answer, which is how am I going to recover after my stroke? So for patients that come to our Miller-Fisher service, which is our acute stroke service, and are on the ward, they ask the question, with regard to arm function, for example, will I be back to everyday life? Will I be moderately disabled, or will I be severely disabled, requiring help all the time and in a nursing home? And I would argue, there have been substantial efforts over the last many years to be able to predict recovery after stroke. But by and large, our ability to predict recovery in stroke and more broadly in acute neurologic disease remains a black box. We're not very good at predicting and prognosis in our field. And I think, to talk about the health systems challenges, this is a challenging scientific problem in as much as it is a challenging health systems problem. Because as you guys know, patients after acute stroke have many transitions in care. They go from acute stroke hospital like MGH to inpatient rehab like Spalding, which is our local rehab across town, to home, and then to outpatient clinic. And traditionally, across these different settings of care, there isn't a quarterback that really follows these patients. And so to address that, we in fall of 2019 launched an AHA-sponsored an AHA-sponsored workshop in which we brought together a multidisciplinary crowd, including physiatrists and neurologists and speech, occupational, and physical therapists. We all met at the Boston, at the Copley Marriott in Boston. And basically, we went through a series of exercises to brainstorm collectively what are challenges that face the stroke recovery system today. And one of the things that came out of that, which we're currently writing up, is this word cloud. And as you can see, many of the words that appear large, which means that they had a greater number of hits, relate to health systems issues rather than science issues. People identified access and insurance and fragmentation of the post-acute stroke system as a major problem. And so really to address this, at MGH, starting in 2017, when I was finishing my training as a neurology resident, we basically launched a research study, which became kind of a flipped care model for recovery after stroke, in which we understood that before we could create new therapies to help people recover, we first needed a framework to understand how people recover and why people recover after stroke. And so what we did was we launched a clinical research study in which all patients who enroll in this study are enrolled in the acute hospital setting. We focused on patients with arm weakness after stroke as a start. And we brought patients back to our research study at 6 weeks, 3 months, 6 months, and a year. And in parallel with that, we also developed a new clinic, which became a model of care in which we're seeing our stroke patients to provide what they need from a stroke secondary prevention standpoint, as well as a focus on their recovery. And so we see patients in the hospital 6 weeks, 3 months, 6 months, and a year. And what the research study does is that we collect a series of outcome measures that quantify their recovery over time. And it took a multidisciplinary team to do this. And so that's our first kind of major point, is that this kind of clinical research effort really takes a lot of buy-in from a lot of different divisions and departments. And I think at MGH, one thing we've been successful at doing is getting people excited about the mission of taking care holistically of stroke, of patients with stroke, and focusing on their recovery. And so we launched our research study, which is called SMOT for Boston with the H. Essentially what it was that we're focused again on collecting outcome measures over time for people with upper extremity arm weakness starting during the acute hospital stay. To date, over 3 years with a little bit of a break because of COVID, we've enrolled 140 patients. I will say that the measures that I will show you in a second are time intensive. They include the Fugl-Meyer upper extremity. And a lot of this has been done in person to date, and we're now sort of rethinking in the COVID era, how do we collect a set of outcome measures remotely that would be meaningful for the field. So the primary goal of this study, which was broad to start, and this was at the time, which I'll talk about later, when John Krakauer and others were also thinking at Hopkins about how people recover after stroke. And so we at a very broad level, we just wanted to understand what are trajectories of recovery after stroke. What determines whether someone is going to start out nearly plegic and recover very well versus recover moderately versus have no recovery at all. And so to do this, we started to think about, well, what outcome measures do we need to collect? And as a neurologist, sadly speaking, as a neurologist, we don't spend a lot of time thinking about outcome measures after stroke, nor about recovery, really, traditionally. And I spoke to one of my mentors at UCLA, Steve Kramer, and he said, well, if you want to collect outcome measures across stroke, one thing that would be relatively novel is if you started to collect outcome measures that span the ICF domain. And I said, well, what's the ICF domain? And that's sort of embarrassing from a neurology perspective, but I think that's one of the shortcomings of our field, in that, as neurologists, in a very different way from PM&R, we don't learn about structures for thinking about disability. And so when we designed this study, we collected outcome measures that span the range of the International Classification of Functioning, going from impairment to activity to participation. And this is just a list of the outcome measures that we started with, including the Fugl-Meyer grip strength NIH stroke scale for impairment, box and blocks, a 9-hole peg and Barthel index, and the Rankin scale for activity, as well as for participation. We asked questions how they were doing in their everyday life over time. Over time, this study has broadened as we've gotten continuing input from our occupational and speech and physical therapists, and we've brought in our outcome measures to include measures of gait, as well as measures of cognition, because we've realized that upper extremity motor recovery doesn't occur in a vacuum, and that in order to really understand upper extremity motor recovery, we really have to start thinking about cognition and other aspects of recovery. So this research has taken a lot of time to build the team to be able to do this. And I think that's one of the first points, is that people collectively at MGH have recognized that this is that stroke recovery, the health system problem, and that if we could collect outcome measures, we could start to address that. We wrote up this paper in a journal that was published in 2019 that basically just talks about the challenges of collecting standardized outcome measures over time, specifically on the acute stroke ward, when patients are cognitively impaired and sick, and when occupational therapists and speech and physical therapists have demands on their time. And so this is a person in our clinic who we did the Fugl-Meyer on. Okay, so that's broadly speaking just to say that health systems is a problem in recovery after stroke, is as important, as challenging as the science. So now I'm going to talk a little bit more about the science, outcome measures, and biomarkers. So as you guys know, there's a rich science behind recovery after stroke that spans cells to circuits to behavior. So in acute stroke, there are significant changes that are happening within minutes to hours after stroke that span cell death and inflammation, to changes in network function, to rapid changes in behavior. In stroke, and this kind of we learn a lot about as neurologists. In stroke recovery, there's also a rich biology, and I would argue that at a fundamental level, when we're talking about stroke recovery, we're fundamentally, I hope, talking about biology. And so at the cellular level, there's changes in blood vessels and neurons and synapses. At the cellular level, there's shifting cortical activity, and at the behavior level, there's longer term changes in behavior. And one of the things that we have to stress in neurology to sort of our colleagues is that stroke recovery and acute stroke are different. And stroke recovery is different from, is really, if you're targeting the biology of stroke recovery, you're targeting an inherently different biology. And so this is a diagram from Tom Carmichael's lab at UCLA, who runs a stroke recovery animal lab. And there's a lot going on in this slide, but this is just to say that in the biology of stroke recovery, which this is not a talk about, there's rich changes that occur at the cellular level, at the blood vessel level, that are representative of what happens during recovery, as well as what happens in terms of cancer programs, as well as what happens during normal development. So this is one of sort of my favorite studies to talk about, because I think this is one of the unequivocal demonstrations that plasticity occurs in the brain after stroke, and one of the unequivocal demonstrations that rehabilitation actually affects plasticity. So these are classic studies from Randy Nudo that were published in Science in 1996. And when I think that when we think about neuroplasticity as a field, many of us think about these papers. And so what they did in these papers was they induced a stroke in a monkey in the middle cerebral artery. This is showing the artery. This is pre-infarct. They occluded one of the arteries. And then they mapped out with electrical stimulation the different parts of the primary motor cortex that represent different parts of the upper extremity, including the digit, the wrist and forearm, etc. And basically what they showed was that if you compare pre to post infarct, there's a change in the representation of upper extremity after the infarct, meaning that parts of the upper extremity that subserve the digit shrink and parts that subserve more proximal parts of the upper extremity grow. And then what they went on to show in a separate science paper that same year was that if you give the monkey rehabilitation, increasing, which in that was basically moving the monkey's affected arm, that you could actually preserve parts of the motor cortex that are subserved by parts of the upper extremity. So the parts of the primary motor cortex that are used for the digit after rehabilitation did not shrink as much as they did if you did not give the monkey rehabilitation. So I think again, this is these studies in monkeys are unequivocally showing that that stroke changes cells at the level of the motor cortex, and that if you give rehabilitation, that you can preserve the representation of the motor cortex. And you know, there's been decades of research that has happened since then, and I would argue that much of what we do since then, with very fancy tools like fMRI and high-density EEG and TMS, et cetera, are basically a proxy for that, in that we're trying to map changes that are happening in the brain through different signals, including BOLD and EEG, et cetera. But really what we're really interested in at a plasticity level are changes in the map of the motor cortex and other parts of the brain. And so this is fMRI research. This slide summarizes a lot of fMRI research that has happened in the past 2 decades. And basically, one of the themes that people find when doing fMRI in patients with stroke is that when a healthy control attempts or moves their right upper extremity, the left primary motor cortex lights up. But when a stroke patient who has had a stroke of the left side tries to move the right upper extremity, the activity shifts more toward the ipsilegional arm, meaning the arm that's on the hemisphere that's on the same side as the arm moving. And the timing of this shift, the reason for this shift, and the role for this shift is debated. Whether it's actually adaptive or maladaptive for recovery is something that's hotly debated. But what people have shown is that the amount of shift that happens from ipsilegional to contralesional hemisphere is directly related to how much of the cortical spinal tract, which I'll talk about in later slides, is damaged. So meaning the more severe the stroke is affecting the arm, the more that activity shifts toward the other hemisphere. So I'm now going to talk about these concepts of biomarker and outcome and recovery and how I think about them. And I think it's very important in our field of stroke recovery to be very clear about what we're talking about here. So, so an outcome measure is sort of how a person is doing at a cross-sectional point in time. Recovery, if we're talking about recovery, really measures a delta in my mind. So it's measuring a change between how someone is doing early on and when we measure the outcome. And then a biomarker, which I'll talk about again in a subsequent slide, really is, it has actually a strict definition by the NIH, but really is trying to map on a biological process to a recovery process. And so the NIH convened a work group in 1998, and basically they defined a biomarker as a characteristic that is objectively measured and evaluated as an indicator of a biological process. So there are different types of biomarkers. There's everything from a monitoring biomarker to a diagnostic biomarker to a response biomarker to a predictive biomarker. And I'll talk in subsequent slides about in recovery after stroke, what's unique is that many of these biomarkers were defined in terms of cancer, because in cancer, what often happens is you're trying to follow a patient as the cancer progresses. And so you measure something either serially or at the start, and you're looking for something that tracks with disease progression. What's different in thinking about spontaneous recovery after stroke, meaning recovery in the first 3 months, which we'll get to in a second, is that instead of monitoring decline, meaning that the disease is progressing, we're actually monitoring recovery. And that's sort of unique. And if you look at the literature in biomarkers after stroke, many of the terms that we use are actually quite conflated. So I just want to point out that there is a strict, that the NIH has defined what a biomarker is. Applying it to the field of stroke recovery has actually not been done that rigorously yet. And so in terms of thinking about biomarkers of arm motor recovery after stroke, a lot of what has been done so far has focused on the corticospinal tract, both in terms of thinking about predictive and prognostic biomarkers and response biomarkers. And I define a predictive prognostic biomarker really in thinking about spontaneous biological recovery, which we're going to talk about in a second, and a response biomarker is thinking about what happens to a patient after you give a treatment. But regardless of either of those two themes, a lot of what's been done so far has really focused on the corticospinal tract and really structure and function of the corticospinal tract. And so what people have done so far is they've used transcranial magnetic stimulation to map whether a patient is MEP positive or MEP negative. And basically what you do is you do a single pulse over the affected hemisphere to map out whether someone has a motor evoked potential, which you measure in the affected arm in the FDI muscle. And basically there are studies that show that if you're MEP positive, you're much more likely to recover than if you're MEP negative. Similarly, people have mapped out the corticospinal tract using high resolution imaging by looking at the fibers and comparing the fibers of the corticospinal tract from the affected arm, affected side to the non-affected side. And they generally look at a ratio of the number of corticospinal tract fibers that exist in the fiber bundle. I will say that both of these overall techniques, while very exciting, take a significant time and effort, take dedicated machines like a TMS machine, which is not necessarily in the US available clinically, or for MRI, take extra scanning time and dedicated sequences, which as everybody knows, for stroke patients is actually very difficult to do at scale. So, so our first study, I'm now going to talk about the first study that came out of our database that we have created, which I talked about sort of how we created that in the first few slides. But the first study that came out of our database really was looking at structure of the corticospinal tract and whether we could relate structure of the corticospinal tract to recovery after stroke. So this was 6 strokes that I saw as a resident, all causing arm weakness. And as you can see, strokes affect different parts of the brain, from the more cortical parts to the deeper parts. So the primary hypothesis for our first study was basically that we wanted to kind of take these themes that had been percolating in the research fields and basically ask the question, could CST injury from acute stroke images, which most all patients get when they come to MGH, could that predict upper extremity recovery in the first 3 months after stroke? Meaning, could we use it as a biomarker for upper extremity motor recovery in the first 3 months? And then I'll talk in subsequent slides about sort of how we did that. So from our database, in a prospective way, we took 65 patients with upper extremity weakness after ischemic stroke. All of them again had acute MR images, and we did an initial Fugl-Meyer within the first week of stroke, and then we did a repeat Fugl-Meyer at 90 days. And there were a few patients that dropped out or who passed away in between the time, and we included 48 participants in our final analysis. And so these are upper extremity Fugl-Meyer scores. So the Fugl-Meyer score is a 0 to 66 point scale, 66 being perfect, 0 being plegic, that measures motor synergies of the upper extremity. We just use the motor component. And so this basically just shows what the Fugl-Meyer was on hospital admission and what the Fugl-Meyer was at 90-day follow-up. And you can see here that there are sort of two patterns of patients that emerge. There are patients that start out sort of mild to moderate and recover very well. There are patients that start out severe and actually recover very well. And there are patients that are severe that hardly recover at all. And so another way to plot this, the same data, is to plot it the following way, in which you're looking at the x-axis here is the potential for recovery. That's just 66 minus the initial score. So it's basically initial stroke, initial Fugl-Meyer. And the y-axis is the actual change in Fugl-Meyer, which is how much they actually recovered between 0 and 90 days. So this is actually the same data that's shown in a different way from this graph here. And what John Krakauer and others had shown previously, starting with a paper I think in 2006, was basically that if you do a cluster analysis on your data, looking at this group of patients, there are essentially two clusters that come out. Really, and the way that they found this was basically if you do a linear regression, looking at many different factors that predict change in Fugl-Meyer, one of the most robust things that comes out is initial Fugl-Meyer score. And so this gave rise to this kind of rule, which is called the proportional recovery rule, which I'm not seeing everybody's faces on this call, but which has come under a lot of heat recently, which I'll talk about in a second. But basically what the proportional recovery rule says that it is on average, people tend to recover proportionally to their initial deficit, and they tend to recover. And if you do that linear regression, the regression factor is 0.7. So meaning that people tend to recover 70% of their available recovery. And so this gave rise to many different papers in the field that basically started talking about sensory recovery and neglect recovery and gait recovery. And people started to extrapolate from this that potentially there are fixed mechanisms for which people recover after stroke. And basically, it doesn't really matter what you do in the first 3 months. People either recover proportionally or they don't. Now, this has been the topic of many debates at stroke recovery conferences. And there are all sorts of statistical sort of problems with modeling a change score by an initial score that I'm not going to get into right now. But just to say that the story is likely much more complicated than proportional recovery. It's not just that there's this binary rule and that patients recover on it and patients don't. And I don't think from talking to John Krakauer that he actually intended it for it to be a prediction rule. But in relatively small data sets like n equals 48, it provides a good way to start to model the change. Because if you really wanted to do this in a big way, you need a lot of Fugl-Meyer scores on the span of hundreds. And so in relatively small data sets, I still do think that there is something to thinking about people that achieve proportional recovery versus not. So that's what we did in this study to start. So basically, we modeled people that proportionally recovered versus those that didn't. And there were 31 people that proportionally recovered, 17 that didn't. And as expected in this initial table, the patients that proportionally recovered had lower NIH stroke scales than the limited recovers. They had higher Fugl-Meyers than the limited recovers. And their outcomes at 90 days were better than people that did not achieve proportional recovery. And so basically what we did to start was we asked the question, well, can we take lesion masks that, since we get MRIs on everybody who has acute stroke, can we take lesion masks, extrapolate the corticospinal tract injury, and then use it to predict who's going to recover and who's not? So we took our MRIs, we transformed them into standard M&I space. And then when you do that, you can put them into MATLAB and ask all sorts of questions about different parts of the brain that the lesions overlap. And so this is showing, so the first thing, this is showing two different corticospinal tracts, the blue and the green. The green track is actually the Johns Hopkins CST tract. I don't actually know the origin of that, but It's available in FSL, which is an imaging program. And the blue track was provided by Steve Kramer, one of my collaborators and mentors, in which they scanned 17 healthy participants in a DTI scanner and created their own version of the corticospinal tract. And as you can see here, people can't even agree on where the corticospinal tract in the brain is on a template. So that's one problem. But regardless, if you look at these two people, one person had a big stroke, one person had a little stroke. This person had a big stroke that spared the corticospinal tract largely. This person had a relatively little stroke, but hit the corticospinal tract pretty much straight on. And the person that hit the corticospinal tract straight on had almost no recovery. The person that hardly hit the corticospinal tract at all had very good recovery. And so there turns out also, in addition to not agreeing on methods for calculating for where the corticospinal tract is, turns out that people also can't agree on how to calculate injury to the corticospinal tract. Without getting too far into it, when you have a stroke lesion in 3 dimensions and you have a corticospinal tract also in 3 dimensions, you simply overlap the voxels on top of each other. You're going to double count voxels, because if you believe that the corticospinal tract is a bundle of axons that goes from primary motor cortex with one cell body down to the spinal cord, then if you overlap it multiple times, that's not going to work. So there are different techniques for actually, when you have your stroke lesion mask and you have your corticospinal tract template, actually calculating how much injury there has been done to the corticospinal tract. One method is just taking the Z-slice and overlapping it. Another method was developed by Gottfried Schlaug and others in Boston, in which they came up with something called the Rahn weighted corticospinal tract lesion load. And another method was developed by Steve in his papers, in which basically you split the corticospinal tract into 16, which is an arbitrarily picked number of axons that are descending. And you ask the question, how many of these 16 axons were cut by a specific amount? And if you've injured that spaghetti strand by a specific amount, then you just take out that spaghetti strand completely. And so when this started, we just said, well, let's just implement all of them and see which one wins and see if there's a better one. So it really started as a methods paper. And so that's what we did. Turns out that the answer is that it doesn't really matter what you do. So it turns out that for proportional recovery versus limited recovery, those people that recover proportionally versus those that don't, if you do a logistic regression controlling for lesion volume, that it doesn't matter what method. So these are the rows are the different methods, and this was the amount of injury, and then this was the p-value in between proportional and limited recoverers. And so it turns out that all of the methods could distinguish proportional from limited recovery. When you ask the question, well, how good of a classifier is it using ROC analysis, you get the answer that it's pretty good, but not great. So you get AUC values ranging from 0.7 to 0.8, which is good. Probably not good enough for clinical prime time yet, but okay. And then if you divide people based on quartiles of CST injury going up, you see that you have less proportional recoverers and more limited recoverers. Again, it's not perfect. So it's very good at distinguishing people that it's very good at distinguishing people who have little CST injury. They're going to probably proportionally recover, except for one exception. But for those that have severe CST injury, it's actually not that great. There are 3 outliers out of 9. So then the real question is, at an individual level, how good is this, right? For an individual, if you do a regression, controlling for initial injury, then how good is the corticospinal tract at telling you what the delta is going to be? And it turns out that it's not great. The R squared is about 20% of variance. So basically the take home from this initial study was that regardless of tract or method used, we could explain using acute stroke MRIs and template overlap with CST about 20 to 25% of variance in the change in Fugel-Meyer score between 0 and 90 days using these methods. And so there again, there are all sorts of caveats about using acute stroke neuroimaging. Does it actually represent the final infarct burden, et cetera, et cetera? But the great thing about this is that it can be done at scale. It can be done on retrospective data sets. It can be done on clinical trials that have already been done, et cetera. And it provides a way to start to stratify people into different buckets based on their recovery potential. Okay, so that's my biomarker spiel. I'm going to talk about outcomes now. So as I mentioned before, we collect multidimensional outcomes for recovery after stroke. So this is one way that we started to visualize this. This is a polar plot, and all of these scales are normalized from 0 to 1 on their outside level, essentially based on the ceiling of what these scales are. And I've color-coded here, we color-coded here the different axes of the ICF. This is impairment, activity, and participation. And this is just to show, and the different sort of shapes show the different changes over time, what in the first week, 6 weeks, 3 months, and 6 months. And this is just to show that recovery is multidimensional. And just because one person is recovering in the impairment domain does not mean that they're necessarily recovering in the participation domain and vice versa. And so this is just 4 patients, and this very clearly shows that if you just think about this shape, it's not the same for everybody. And so it shows that, you know, if we're targeting rehabilitation strategies, we potentially need to think about them more holistically. So we've thought a lot and haven't gotten to quite closure on how to quantify this. But one or two methods of starting to do this are the following. So one kind of story that we're putting together now is that we're starting to look at the concordance of different outcome measures. And so this is a story about outcome versus recovery, and sort of what are the different outcome measures that we're using in stroke recovery trials. And so again, for acute stroke people, the modified Rankin scale is sort of gold. And the modified Rankin scale is a 0 to 6 scale, with 6 being death and 0 being being nothing at all, and 1 to 5 being everything in between. And you'll see here that if you map on the outcomes of Fuglemeyer and Box and Blocks and Barthel index at 90 days over the outcomes of Rankin at 90 days, you see that there's a significant distribution of people who have a lot of variance in their Fuglemeyer outcomes, especially in the 2 and 3 range. And this is just saying that the Rankin scale is not capturing in a sensitive way upper extremity motor recovery, meaning that people can recover significantly on their Fuglemeyer and completely be missed if you're just classifying them as a Rankin of 3. And so another way of thinking about this is thinking about the change in between 0 and 90 days. So in the previous slide, I'm just talking about outcomes. Here I'm talking about actually the change between 0 and 90 days. Did people achieve concordant change? And so the way we're thinking about that is there's a concept known as the minimally clinically important difference, which is the smallest amount of change in an outcome scale that a patient perceives as clinically meaningful. And this is established in different ways and all sorts of caveats, et cetera. But it's the MCID is typically used to assess progress through the continuum of care, establish benchmark, and to assess the effectiveness of different rehabilitation therapies. And so what we did here was, so for the Fuglemeyer, the Box and Blocks text, the Barthel index, and the Rankin, we've listed out the proportion of people that achieve MCID. And then we looked at those that achieved MCID on one scale versus those that did not achieve MCID on another scale. So if all the scales were perfectly concordant, then all of these would be 0. But as you can see, there's quite a number of people who are achieving MCID change on the Rankin scale, but not achieving MCID change on the Fuglemeyer, as well as vice versa. Finally, just to talk about outcome measures, another thing that we started to explore are different trajectories of recovery. And so one way we started to do this is looking at the MCID. And so a graduate student who works closely with me basically took about 40 of our patients and split them up into patients that recovered MCID in the first 6 weeks versus those that did not. I'm sorry. The red are patients who recover the MCID in the first 6 weeks. The green are patients who recover MCID at a later time point after 6 weeks. And the blue are people who never achieve MCID. And basically, she looked at the number of therapy hours between these 3 groups: fast improvers, extended improvers, the green, and limited recoverers, the blue. And she asked the question, well, does the number of therapy hours differ between these groups? And it turns out that there's a difference between the fast and limited group, but there really isn't a difference between the extended and the limited group, meaning that the patients who have an opportunity for recovery are potentially not getting therapy in a way that they need. Okay, so I'm last in our outcome measures part going to be talking about a story that we're developing that's focused on choosing the right outcome measures after acute stroke. And so here we're looking at performance on the box and blocks test versus the grip strength test. And this shows the affected or contralesional upper extremity, and this shows the ipsilesional upper extremity, the traditionally non-affected upper extremity. And so if you look at the contralesional upper extremity, you'll see that the y-axis here is normalized for age-matched, gender-matched controls. And so therefore, everything has been converted to a z-score on the y-axis. And what you'll see here is that as expected for the contralesional upper extremity, there's recovery over time. You start out at very severe z-scores, -7 z-scores, and there's recovery between 1 week and 6 weeks, and 6 weeks and 3 months. And if you do a repeated measures ANOVA between these time points, they're highly significant, meaning that the affected arm recovers over time for both box and blocks and grip strength. For the ipsilesional arm, what's notable is that it's actually, and there is literature, a significant amount of literature to suggest this. The ipsilesional arm is actually not normal after stroke. And there actually also is recovery of the ipsilesional arm in the first 3 months. But if you compare grip strength to box and blocks, now if you look at the rows and the differences between the second row and the first row, you'll see that the grip strength scores, even though normalized for age and gender matched norms, are not as impaired as the box and block scores at all time points. And so our question really was, why is this? Why is it that a task in which patients squeeze that involves muscles of the arm and hand, why is it that that is not as impaired as a task in which patients move a set of blocks? And our initial hypothesis is that this has to do with attention and cognition, because the box and blocks test takes 1 minute of sustained attention to transfer a set of blocks from one to another, while the dynamometer is a task in which you just ask the participant to squeeze, and it's a task that happens abruptly, onset and offset. And so our first hypothesis was by varying the nature of the attentional demands of these two tasks, we could pull out that patients actually after acute stroke are not as impaired on the grip strength task of the ipsilesional and contralesional arm as they are on the box and blocks task. To look at that a little bit further, we did a linear regression where we're asking the question, well, does cognitive impairment explain any of this? We extrapolated cognitive impairment from the NIH stroke scale, which there's a subscale of the NIH stroke scale called the NIHS COG-4. It's not very good, but it's what we had. And so basically we asked the question, well, controlling for lesion volume, does cognitive impairment explain any of the variance in motor performance of the contralesional and ipsilesional arms of box and blocks and grip strength? And it turns out that for box and blocks at T1, especially for ipsilesional extremity, it does. So the beta is significant here, and the model explained 33% of variance for the ipsilesional arm at T1 and 22% of variance for the contralesional arm at T1, meaning that, and it did not do so for grip strength, meaning that cognitive impairment is explaining variance in motor performance early after stroke for the test that's requiring high cognitive demand. We finally mapped our lesions again to ask the question, well, how does the anatomy of injury relate to performance of these tests? And so what we did was a voxel lesion symptom mapping technique, where we basically asked, and that's basically a technique where you can, on a voxel by voxel basis, ask the question, well, for patients that have lesions at that voxel versus patients that don't, what is the difference in performance of the group that has a lesion at that voxel versus a group that doesn't? At the end of the day, if you do that on every voxel in a standardized space, that basically gives you a map that associates anatomical injury to behavior. And so if you do that, we did that for contralesional and ipsilesional box and blocks and grip strength. And so if you do that, basically what you see is that the box and blocks injury that's associated with performance on box and blocks, it's associated with brain structures that are much farther away from the motor cortex and the cortical spinal tracts than we would expect. So it's really involving significant injury to the insula, particularly the anterior dorsal aspect of it. While for grip strength, injury is, although it's still somewhat non-specific, it's much more restricted to the primary motor cortex and corticospinal tract. We can actually quantify the number of voxels that are output by our VLSM that are non-sensory motor versus sensory motor. And so for boxing blocks, there is a much higher percentage of voxels, both for contralesional and ipsilesional upper extremities, that that are associated with performance. And so basically, we're just preparing this for publication, but basically what we're seeing here is that cognition, specifically impaired attention, was our initial hypothesis, can actually confound motor performance starting early after stroke. And the relevance of that is twofold. First, we know that cognition and motor performance are important for functional outcome. But one way that cognition might mediate the impairments in functional outcome is it actually might be directly mediating impaired performance of motor, of arm. That's the first thing. And the second thing is that in thinking about clinical trials and the test that we want to pick for being able to quantify recovery after stroke starting during early in the acute phase, especially when cognitive impairment is very prevalent, we want to pick, if you want to really quantify the motor system, you want to pick tasks that are more selective to the motor system. Okay, finally, in the last 5 minutes, I'm going to talk about sort of how we're thinking about new treatments for recovery after stroke. So as this crowd knows, there's a lot of different treatments that are in the clinical translational pipeline, spanning preclinical development to ready for broad clinical application. These involve biologics to robotics, which there's a robust program at Hopkins for, to constraint-induced movement therapy, et cetera. And the question is, why haven't many of these kind of reached large-scale adaptation? And so I was a postdoc with Lee Hochberg in the BrainGate lab, which, and for those that don't know, the BrainGate lab is a brain-computer interface trial in which intracranial electrodes are implanted into primary motor cortex to allow people to control robotic arms, to type on screen, and to control their own arms and limbs versus electrical stimulation. And this is done by decoding activity in the primary arm-hand area of motor cortex. But more generally, what a brain-computer interface is basically associating a brain signal with, whether that be EEG or fMRI or single unit recordings, with an output with an output device. And that output device can be anything. It can be a robotic arm, it could be an arm orthosis, et cetera. And so there have been small studies in which people have looked at using a BCI arm orthosis for upper extremity rehabilitation. So in a different way from actually a patient using the device constantly. Basically, what the premise of this is that if a patient can't move their affected arm, if they have an EEG attached to them and they think to move, you can actually drive movement of an orthosis. So similar to a rehabilitation session, what you can do is have the participant drive his own arm and hand movements. And people have shown in some relatively small clinical trials that if you do that, you can actually improve the Fugl-Meyer score above controls, and that the fMRI activity, as shown here, shifts toward the more adaptive side, the side that's opposite the lesion. Again, these are early stage trials that have been done mainly in Germany and other places. And so we've started at MGH to build the components of an upper extremity rehabilitation device. We received a grant for the InMotion arm, which was previously the MIT Manus. We've started to collect upper extremity kinematics after acute stroke on our ward. And we're also doing high density EEG recordings for these same patients at the same time. This is just a picture of me in our prototype. And we started, in addition to building this, we've started to look at using high density EEG. We started to look at how different brain regions are connected to each other, because with the high density EEG, you can look at how the signals oscillate in relation to each other. And this is very early work, but basically we're finding that there are robust associations between changes in coherence of premotor to motor cortex with changes in Fugl-Meyer. So, but I think, just going back to the initial slide that launched this section, I think there's a long way to go before we can actually translate both neurotechnology for upper extremity motor recovery, because we don't fully understand yet how to associate neural signals with recovery in the best way possible. We haven't yet solidified the best biomarkers to stratify patients into clinical trials. And we need to come up with a better approach to capturing outcomes after recovery after stroke. And so our vision really, with our natural history study that we've launched in conjunction with the neurotechnology that we're developing at MGH, is really to think critically about outcomes that improve quality of life, to develop biomarkers that can inform where patients go by being able to predict how they do in a clinically relevant way. And then finally, to develop new neurotechnologies that are informed by neural structure and function, everything we're learning about spontaneous, everything we're learning about spontaneous recovery after stroke. So I'll just stop there. I've been very fortunate in my early career to receive a significant. I've been very fortunate in my early career to receive support from both the MGH Neurology Department as well as extramural sources, including the AAN and the VA. This research, as I mentioned, takes a village of people that really believe in this mission. And so this is a picture of our SMART team at one of our retreats. And really, this is a collaboration between occupational physical therapy, neurology, SLP, as well as the MGH Institute of Health Professions. Again, these are some of the people that have helped me with this work, but there are many more to thank. And so I'll take any questions.
Hi, this is Preeti Raghavan.
Hey, Preeti.
David, thank you very much. I think this was really excellent. As you know, we are trying to get our Stroke Institute started, and I think this is inspiration for the kinds of information that can come out of systematically looking at recovery. So kudos to you for putting this all together and really dissecting what it takes to recover from a stroke. It's definitely not straightforward, it's complicated, and I think what you presented really brings that out. So thank you.
Thanks, Preeti. Yeah. Looking forward to working together in the future as well as we've been doing over the past few months. So.
Thank you.
Dr. Lin, I just had a question. I think I was, I'm a physician here in the department. I think, and actually currently I'm attending on the inpatient rehab unit. And I think one of the themes that you really, I think was really highlighted in your talk was, again, this relationship between motor recovery and cognition. I think what I struggle with, though, is cognition is such a big, broad topic. And so when you're talking about somebody being cognitively impaired, that means a lot of different things for a lot of different patients. And so I just wanted to know, I'm sure this is something that you guys have talked about, but if maybe you could provide some more thoughts on that, because I think it's, I think it's something that as a clinician, I definitely see, but maybe to have some more details about how you guys are thinking about that, I think would be helpful.
Yeah, that's a great question. I'll be the first to admit that in my presentation, I kind of hand waved a lot and just said the word cognition a lot. But I totally agree that cognition is a broad, it's not a one size fits all term. There's visual spatial abilities, there's attention, there's executive function, there's language, etc. And they probably all have some sort of synergistic interaction with motor recovery. And I think we're in, to be honest, I've looked into this a lot as we've been preparing this paper. We're in very early stages of parsing that out. I mean, I think broadly as a field, we know that cognition impacts functional outcomes. People have shown that if you collect a MoCA early and then you measure functional outcomes later, that the MoCA correlates with functional outcomes. We also know from neuropsychological literature that cognition impacts motor performance in healthy people. For example, in that literature mainly is from geriatric people, in which if you're looking at motor performance, upper extremity arm dexterity, as attention decreases with age, there are decreases in motor performance. And so, but I think parsing that out in stroke, I think stroke introduces a neuroscience opportunity to look at that, which has actually been looked at very little so far, and I think is a great opportunity for the field. But we're in very early days of parsing that out. The data I presented was really highlighting the role of attention, because the differences we saw it in the box and block versus grip strength task was really an attentional one. So someone has to sustain a minute of a minute of attention to be able to complete box and block, while they don't for grip strength. And the area of the brain that we found in our study, the anterior insula, has been implicated in attention. So that's the story that we didn't have a very detailed measure of attention or cognition in our study applied at the time in the 50 patients in our data set. We've now implemented the CLICKIT, the cognitive linguistic quick battery, as well as the MoCA, as well as a few other cognitive tests. And I think there's a trade-off there between the clinical reality of doing detailed cognitive testing on patients and being able to feasibly do it. So I totally agree with you that parsing the different features of attention is very important. And I think it has very direct relevance for rehabilitation. If we think about arm motor rehabilitation, we could make big progress in the field by being much more specific about the tasks we're having patients do based on their attentional status.
Thank you. And I guess maybe just to follow that up, maybe just one more question. Just again, I'm working in the inpatient rehab setting, and just a lot of these studies that you're presenting are patients, sort of 90 days post-stroke, and I'm seeing a lot of these times these patients that are, maybe 1 week or 2 weeks after stroke. And I just wanted to know, it sounds like, we perhaps there's sort of these two groups of patients, one that are following this sort of trajectory, you kind of gave that equation about the 70%, that's being debated, but then there's this other group that's sort of falling off. And is there any clue earlier on in that first couple of weeks that could maybe indicate, somebody kind of maybe going into that they're not falling sort of in that expected trajectory? Just wanted to know if you had any thoughts or can point us in that direction in terms of that earlier recovery.
Yeah, that's also very, I think that, separately from cognition for a sec, I think that, one of the themes in neurorehabilitation, which hasn't actually been pointed out that much in the literature, but we do a lot of fancy techniques. For example, the best thing right now probably for predicting upper arm motor recovery, as Preeti and others on this call know, is the PrEP algorithm, in which they do transcranial magnetic stimulation to do TMS positive or negative, plus a combination of MRI plus a clinical score. But I think, more robust than that is probably just serial assessments. Like if you did a serial assessment in some way, whether that's the Fugl-Meyer or a test that doesn't take that long, in the first week or two after stroke, and you saw that there are patients that are starting to just show some wrist dorsiflexion, or just starting to go from plegia to, moving in upper extremity synergy. I think that slope of recovery in the first 2 weeks is probably going to tell you more about the trajectory of arm motor recovery in the first 3 months than probably any neurotechnological test. That's my view. Or even better would be if you did that in parallel with serial neurotechnological tests. How cognition factors into that. So the data that I presented was actually the box and block score and grip strength data that I presented from our study was actually collected in the first week after stroke, and then at 6 weeks and 3 months. And what we showed there is, or what we're showing there is that cognition impacts motor performance most in the first week after stroke. And really the point is that that if you're asking people to move blocks for a minute, their actual score might not just be a motor system score, but it's actually other attentional networks that are brought in and reflected in that score. While if you're measuring grip strength, that score may be a more pure motor score. So I think those are a little bit separate things. But I think for predicting recovery, measuring trajectories of recovery, doing interval assessments is probably the highest yield. And then how cognition interplays into that, I think we don't know yet. Like how cognition affects whether somebody develops a change in their first few weeks of recovery, I think is a really interesting question that I haven't seen any answer to in the literature.
Thank you.
Maybe I can David, thanks. Thank you for the talk. It's very, very nice. And just to amplify what David just mentioned is that, so there are a couple of, I think, very important studies that people have been looking into in the neurorehab field. One is from Winston Biblow group, that they do these motor potentials and this idea of the proportional recovers and so on. Although the proportional recovery is a very flaw unless you look at the people who do not recover. But regardless of that, what they found very clearly is a nice relationship between those who are changing in Fulmeyer, those who have a presence of an MEP in the hand early on. So that's kind of a big group that proposed this idea of the MEPs and the PrEP algorithm that David was mentioning. And then on the other hand, you have these very nice studies from Gerd Quakel that follow, a couple of hundred people with stroke and showing that the extension of the fingers of the wrist in the first week, it has high level of predictability of people who are going to be recovering. The MEP in his studies, Gert showed that the MEPs on the ADM may be adding a little bit more of the variance of those who are only moving the hand up. So with just those two things, you have a huge explanation of who are actually going to recover and so on. So like David pointed out, maybe we are going around all the heavy intensity, heavy high-tech stuff, and then we're going back to kind of a little of the basics of that are describing a lot of the variants of who recovers and who doesn't. But so, as a comment, and again, David, thank you so much for the talk. Since I'm talking, just want to ask you, if you don't mind, you show a lot of the data and results, but I was curious about that, that you showed that the number of hours of therapy, whether you're recovering the first week, in the first 3 months, or do not recover, and showing that those who don't recover actually have more therapy hours versus those who recover fast. So because you didn't have a lot of time to present, the questions are you just mentioned the total number of hours of therapy, or because it makes sense. If you're not going to recover, you're going to be in rehab for a longer period of time, so you're going to have more hours of therapy in the patient. If you're going to recover fast, likely you're going to be discharged from rehab, you're going to have less hours of therapy. Yeah. So if you can explain a little bit more about those results, I'm curious to know. Yeah. And the other question with the hours is actual time to task, not just the therapy has been in number of sessions.
Yeah. So I brushed over that. So when patients come back for our research study, we have this form that we fill out with them that asks them how much therapy they've gotten. That's done by a combination of chart review, like we look in Epic if they get their rehab at Partners, MGH Brigham, or if they don't, then the best thing we do is we basically ask them and ask their caregiver how many hours have they received, and it's, I'll be the first to admit it's a gross estimate. And you're probably right. The people that don't recover are probably just those ones that are in rehab, and so they're in therapy for longer, and so they're telling us that they're getting 3 hours of therapy a day. Now, I defer to you, Dr. Selnick, because you have much more experience in this field than I do. But there are a lot of studies that are trying to estimate the quantity and the quality of rehabilitation, including stuff from WashU with Catherine Lang's group using accelerometers. There and stuff with Heidi Shambra, who I think was at Hopkins at some point, but at NYU, who's doing all sorts of body sensors. I haven't seen a good solution to that. I mean, when we write about this, we're like, well, we just ask them, and we kind of say, well, that's the best that we're doing right now. I mean, I think better in our next version, we'd like to have them journal, like actually journal on an app or on paper, like what they're doing. But the engineering, like of estimating upper extremity movement from sensors, that whole field, I haven't seen that yet be a solution. I don't know what your thoughts are on that.
Yeah, I agree. So there is not a consistent, I think some different groups are working on this, and I think that there's a need to have a better assessment, objective assessment of what is actually happening in the therapy and the training exercises. Yeah. So either EMUs or some video form of capturing activity, or so people have, like you said, people have been playing with different approaches to this, and I think, but there's no consistency, and there's clearly those things have not rolled out, in my opinion, like you, I believe, to the clinical practice. So some therapies are, yes, right in, you have a session, you can ask some therapists to write down every 15 minutes what they were doing. So some people have done that, but it's very onerous on the person. So it's not, I don't think today we have a systematic way of objectivizing what the activities are happening within a therapy session.
Yeah, I think it's a ripe area.
Yeah, agree.
Yeah, I'd be curious about too if there are just some units of trying to utilize some sort of fidelity check, or is there a way to check to see if there is a measurement-based physical therapy care that's being utilized, something like that, as opposed to hours. I agree with both of you. One question I had for you, Dr. Lentz. By the way, great presentation. It was really enjoyable. So when you were going over the objectives, the first objective was just sort of characterizing some of the challenges that some of these systems have, these rehabilitation recovery systems have in hospital settings. And then you follow up with biomarkers and talking about different sort of systems level neuroscience ways of addressing the needs of folks who are recovering from stroke. And I wonder if you could speak a little bit more to how some of these systems neuroscience level techniques could address some of those more systems level health services issues that you described, like access or insurance or even quality of care. If you could speak a little bit more to that.
Yeah, that's a great question. I mean, it's a great question. And there's a fundamental disconnect, I think, which we found in trying to launch this study. This is very hard to do in the U.S. as Preeti knows, and the studies in Netherlands from Bert Kwakkel, in which he's followed 500 people and done serial Fugelmeyers by driving a truck to their house. It's very hard to replicate that in the United States, where patients are transitioning across care settings. And to the cynical, everybody's like, well, what is it? It seems almost insurmountable in some ways, the health systems problems. I think the first thing, I am excited about, in New Zealand with the PrEP algorithm, Kathy Steinier and Winston Biblow have been using this algorithm called PrEP, which uses TMS and MRI and the shoulder abduction finger extension score to be able to predict people that recover on the ARAT, the Action Arm Research Test, versus those that don't, and puts them into bins. And they've actually used that and given that prediction to therapists in their rehab settings. And basically, they showed that if you give a therapist in an acute rehab a prediction of how a person's going to do, that the length of stay at rehab actually shortens a bit. So that's one way. I think in the U.S., could we see a future where we do a set of behavioral and neurotechnological assessments within a few days after a stroke, and then we inform where people go in the health system or what they need? I would love to think so. I think that's the natural extension of this work, of all the work that a lot of people in the country are trying to do. So I think that's the first step, is informing discharge destination. And the second thing, which you guys know well in this department, is I do think that being able to somewhat predict stroke and come up with relevant biomarkers that we can scale is a prerequisite to being successful in clinical trials. Because the way that we're running clinical trials right now, at a first pass, we're not even stratifying patients based on behavioral level. Like we're just including all patients with stroke. We're not even saying, well, let's stratify the Fugelmeyer in an intelligent way. I think if we add in, corticospinal tract injury or TMS into these clinical trials, then we can start to say, well, these people will respond and these people won't, or these people respond this much and these people won't. I think that clinical trials in stroke recovery need to head that direction. So I think that those are the two ways that I see kind of the systems neuroscience informing both clinical trials and the care system. Because the other thing is that, I'm speaking to a group of physiatrists who knows this well, but, if you talk to OT and PT and SLPs, their clinical practice is built much like our neurology exam is, right? It's a clinical thing, and there's not an objective, quantifiable approach that's standardized. And so saying that we're gonna standardize therapy in some way, we're really far away from that.
Great talk, Dr. Lim. Just wanted to highlight the importance of something you mentioned about the relevance of choosing the right outcome measure after stroke. And from where I sit, I've been doing vocational rehabilitation for the last 22 years. And one of the great macro outcome measures, the measure that emerges long after the continuum of care is near completion, is whether people return to work. And I think what's brilliant about your research and your work and our group here at Hopkins is that it's marvelous to know that these outcome measures, these objective measures all add up to some wonderful large outcome later on, whether it's person returning to work or person returning to their role as a caretaker or a homemaker. So thank you very much. I was wondering if you had any specific thoughts about macro outcome measures.
Yeah, I think you hit on it, precisely. I think the measuring outcome measures is key, and picking the right ones. I think, thinking about what are the outcome measures that are clinically relevant is key. Are we going to come up with a new outcome measure for recovery, like the Wolf Motor Function Test? I'm not sure if the answer is that. Maybe the answer is doing a panel of outcome measures that people agree on, that span the ICF and that collect outcomes across different domains, and then integrate them in a mathematically and functionally relevant way is the way to go. I was inspired by the recent Queen Square Nick Ward paper, in which they did this intensive therapy session, and they gave people many hours of therapy in the chronic stroke setting, and they measured outcomes across many different domains. And I think that's what made that study so powerful. But I agree that understanding how outcome measures map onto each other, and understanding which one, and being very clear about the ones that we're measuring for the purpose of systems neuroscience, as well as the purpose of understanding function, is really important. And I think that in neurology, we tend to lean more towards just measuring the Fugl-Meyer, because that seems to map onto systems neuroscience. But I think to do that alone is a little bit short-sighted.
Thank you.
Well, thank you, everyone. This has been very interesting. Thank you, David, for a very exciting talk and an exciting discussion that followed. Just for everybody's information, we are now collecting standardized outcomes across the ICF domain at regular intervals, just clinically, as part of the Stroke Institute. And I think we would be able to have a lot of synergies with some of the work that David has already done. So again, thank you very much, everybody, and enjoy the rest of your day.
Thanks, Preeti. Thanks, everyone.